So, we will continue with our discussion on delta modulation, and here is the diagram we were discussing last time to explain qualitatively the two major types of distortion or noise in a delta modulation scheme. The first one, as we noted, is known as slope overload distortion, which ultimately results in some kind of undesired signal. Sometimes we also call it as slope overload noise, okay. But actually it is a distortion on the signal because the system is not designed properly, the step size has not been adjusted properly, okay. And the other kind of distortion which we usually call as noise is known as the granular noise. And we remember that the slope overload distortion is likely to occur when the input signal changes very fast over a small interval of time, okay. That means, if the slope of the input signal is very high, okay, it needs adjustment in the step size, okay. This is what is exploited in a modified version of delta modulation scheme, which is known as adaptive delta modulation, ADM, which we will not discuss for lack of time basically. Anyway, we will try it out a little bit in the laboratory. Now, coming back to this basic delta modulation scheme. So, one thing is obvious is that if I have to overcome, or if I have to reduce this effect of slope overload distortion, then we should increase the step size, so that the approximate staircase signal catches up with the signal, even though the signal may be varying very fast, okay. So, in general, to reduce or eliminate the slope overload distortion, one should go for larger step size, okay. Whereas, we can see that the input signal, which is basically unconstrained, may not be varying very appreciably over a long interval of time, and because of this kind of feature of the input signal with a larger step size, we may get a resultant granular noise, where the staircase approximation will be rather gross when the input signal is not varying much. So, to contain the granular noise, then one should reduce the step size as much as possible. So, there are two conflicting requirements. For avoiding slope overload distortion, the step size should be increased, whereas for reducing the effect of granular noise, the step size should be minimized, okay. Now, we will have a discussion today, wherein we will try to avoid, we will find out a condition for avoiding the slope overload distortion, and assuming that slope overload distortion is controlled, is eliminated effectively, we will try to assess this resultant granular noise and try to find again some parameter like SQNR, signal to quantization noise ratio, and we will try that again through an example considering a rather simplified sinusoid modulating signal or input signal. Well, one point before I go over is that we can see that when in the staircase approximation of the signal, the step size increases when the signal is increasing, isn't it? And when the step size increases like this, we can see that the slope remains constant, okay. So, we can say that the staircase approximation approximates the signal in a linear manner, the slope is constant over here. Because of this feature, this delta modulation is also called sometimes as linear delta modulation or LDM, to differentiate it further to what I was mentioning earlier as adaptive delta modulation, where the step size, as you can guess now, okay, something similar, something analogous to non uniform quantization, okay. The step size need not be same really. By sensing that the input signal is rising very fast, okay, one may like to increase the step size during this region of the input signal, okay, like instead of this step size getting limited here, you might like to increase it to this point, okay, because you have sensed that there were increases in one direction in the step size for last two sample intervals. So, in the third sample interval, you may like to increase the step size through some adaptation in the feedback path really. So, there will be some other additional element other than the simple delay unit, and then again you find that again the difference between the staircase approximation and the actual signal is still of the same polarity as it was earlier, and hence here you would like to increase the step size even further perhaps compared to the earlier step size. The earlier step size was this much, you would like to increase even further, so that you catch up with the input signal very faster compared to a linear delta modulation scheme, okay. So, effectively you may like to vary the step size depending on the requirement, and which may result in some kind of, if I now join the midpoint of the steps really, the slope would increase gradually, and hence that is no more a linear delta modulation scheme. Okay, that is what is done. A similar thing can be tried out to contain the effect of granular noise. Whenever you are finding that the bits are flipping, the output bits are flipping, really the sequence is 1 0 1 0 kind of thing, you would like to reduce the step size from here. Say here it was 1 0 1, you would like to adjust here, perhaps you would like to reduce the step size here. Then if it catches up, it's fine. If it does not, you would like to, or if the polarity is the same as this one, then you would like to reduce it further. Like that you can very approximately track the input signal, and as a result the overall quantization error can also be reduced. So summarily, if you go for adaptive delta modulation scheme compared to linear delta modulation scheme, you can expect an overall improvement in signal to quantization noise ratio. Okay. But anyway, we will continue with our discussion on linear delta modulation. Now we will try to find a condition for avoiding the slope overload problem, because this is something peculiar to delta modulation. Note that I am making use of one equation which we have already discussed in the context of DPCM. Please refer back to equation number 4 of our DPCM analysis. For quick reference, to save time, I will reproduce the corresponding equation, that particular page. Okay. So you need to start writing only after I show you that equation number 4 for the DPCM analysis was like this: UKTS was XKTS plus QKTS. Can anybody briefly tell me what was UKTS? Kth input to the predictor. Okay. XKTS was the kth input sample, speech sample. Okay. Kth I am saying. Okay. And QKTS was the kth quantization error. Is it not? So I am making use of this equation, and then I am reproducing here as well. Really, this is the equation, fine, which we have already seen. So UKTS was XKTS plus QKTS. I can use this expression even for DM really. And now using equation 2 of our DM analysis, which I presented last time in the last class, you can quickly verify from your notebook. With some rearrangement in equation 2, okay, we can write that U k minus 1 Ts, k minus 1th input to the delay unit, okay, is nothing but x of KTS minus EP KTS. In equation 2, in the direct form, I had written an expression for EP KTS. Okay, so just by changing the terms here this way, that way, you can verify that yes, I can write equation 2 like this. Okay. And then making use of this equation number 7, which I reproduced really, I can express equation 2 like this, or ultimately the EPKTS, which is nothing but the input to the quantizer, okay, is the difference between the kth speech sample, kth sample, and the corresponding output from the delay unit, okay, is x of KTS minus x k minus 1 Ts minus q k minus 1 Ts. Please take some time to verify that this is okay. Okay. So what does this expression tell me? It tells me that the input to our single step quantizer, that is E of KTS for delta modulation, delta modulator, is, I can now interpret, it has got two terms really. First part is this one, the other part is small q of k minus 1 Ts, okay, the previous quantization error. The present input to the quantizer, okay, is the difference of two most recent input sample, okay, minus the previous quantization error. Okay. Now with some assumption, if I assume that my quantization error is not much, the step size is adjusted appropriately, then I can approximate equation 8 to write that EPKTS, let me remind you that this is the input to the quantizer, which is a single interval quantizer, okay, binary quantizer or comparator essentially, okay, is approximately the difference of the present sample and the previous sample. So, this is a good observation point. We can say that qualitatively that the quantizer input for the LDM scheme, okay, one can just think a little bit and can perhaps support that for an adaptive modulation scheme this approximation is even better. The quantization error is even less because we are adapting the step size. Anyway, for the delta modulator, the quantizer input is essentially almost the first backward difference of the input signal delayed by Ts. Backward difference, by that I mean it is x of kTs minus xk minus 1 Ts. Okay, the present sample minus the previous sample value, the difference is essentially the present input to the quantizer approximately. Okay. Now, this observation I can use for finding a condition for, please let me know if I am going fast, the condition for avoiding slope overload. One can guess intuitively that to avoid the slope overload condition, if I say that okay, I mean design a delta modulation scheme which must avoid the slope overload condition, then what is the first approach there? Because as we discussed some time back, the slope overload error is basically related to the slope of the input signal. Okay, higher is the slope of the input signal or the maximum slope of the input signal, okay, you perhaps have to go for a larger step size. Okay, and so I can put it in a different, somewhat different manner, that u of kTs input to the delay unit, which is the output from the delay unit after one interval, okay, it must catch up even while the slope of xt is maximum. That means, if I know the maximum slope of the input signal, then I can write a necessary condition, okay, for which I can even catch up this maximum EP of kTs. EP kTs just now we saw as the first backward difference of the two consecutive samples. Okay. So, the necessary condition for avoiding slope overload altogether is that S by Ts is greater than equal to dxt dt max. I expect some doubt here whether it is S by Ts or 2S by Ts. That's your point, isn't it? Yes. See, just to facilitate this discussion, I have redrawn the quantizer characteristics here. You can see that the two levels, allowed levels, I indicated as plus s minus s, so that the step size delta was twice of s. Okay. Now, dx of dt for the maximum situation when this slope is maximum, we are now talking about catching up by adjusting the step size. Okay. So, the change has to be such that the change is greater than dx dt max, that is the condition. Okay. Dx dt in this case means, what does it mean? The change in the input signal over one interval. Okay. So, xkt is minus xk minus 1 ts by del ts of course. Okay. So, the change d of xt is del of xt is xkts minus xk minus 1 ts really. Okay. Now, one can see that if previously the step value was here, okay, it needs a change only this much for a change to the other level at the output of the quantizer. The input signal has to change by an amount half of the step size basically, which is s. to make a change in polarity, or in a sense to say that it has caught up, the staircase approximation has caught up with the input signal. Okay. It is not necessary that this the value, the staircase approximation has to change by twice of s, it has to change only s, a little bit more than s value, and then by the quantizer characteristics it will be read, any value here or here will be read as plus s, so that the quantizer output will catch up. So, the change that is necessary is not to the extent of 2s really, it is only s. So, it is sufficient that s by Ts is greater than dxt dt maximum. Is that okay? Say if this is a moment when the slope is maximum for the input signal, okay, then the difference dxt is essentially this amplitude difference, isn't it? Okay. Now, when I say slope overload is controlled, I mean that the staircase approximation has caught up with the input signal. Okay. That means, if I go back briefly to this diagram really, it is somewhere here, or it has exceeded, just like that, it has crossed the polarity of the input signal. So, whenever there is a change in polarity in the quantizer output, because the quantizer is a 2 level one really, okay, the slope overload is overcome when there is a change in polarity at the quantizer output. We can see that the quantizer output was say 1 1 1 1 and then it will become 0 here, because the quantizer output the staircase approximation has exceeded the actual signal value. So, slope overload is avoided when there is a change in polarity at the quantizer output, isn't it? Now, for changing in polarity I can see from the staircase, if this is my previous staircase one, if I was here, okay, then for changing the polarity I do not need an amplitude change, step change of twice s. A change in value in the staircase of only s is sufficient, because the quantizer for any value in this range, okay, so long as the value is positive really, it will give a change in polarity at the output really. Okay. So, the change in step size that is necessary is s, not 2s. So, the staircase approximation has to change by s over the sampling interval Ts. So, s by Ts should be greater than this maximum slope. Okay. Now, yeah.
The derivative we are taking here,
Hmm.
will it be the derivative of the continuous function?
No, not
Or
not
average
really.
I mean the average slope between two instances of the time, like when we are taking the step, whether it is going up or down.
You need not take the average even, you take the maximum value wherever it is. Okay, when you are designing, okay, see again, it is not very important to be very particular here, because see already for this kind of derivation we have made an approximation that the quantizer input E p kts is approximately the backward difference. We have neglected the quantization error q kts. Okay. So, on that we are developing a basic expression. So, at the first level of approximation is this one, and here the maximum slope in between the two sampling instants, wherever the slope is maximum, consider that value. Okay. No averaging is necessary here, okay, for this linear delta modulation. Yes.
Simple input output characteristic. If the signal is to the left, it is pluses. If it is to the right, it is minuses.
Right.
So what is this that even if it exceeds by pluses, then it can go up?
This needs a discussion with respect to this diagram really. See, this is the staircase approximation you are getting from the delay unit output, okay, and this is the actual signal sample really. So, suppose this is the sample instant we are talking about. If this is the k minus 1th sample, okay, the actual sample value is here, okay, the staircase approximation from the delay unit output is here. So, what is going to be the polarity of the output? Is still going to be positive really. So, what we expect is that, what we can say is that at the next interval the delay unit output is going to increase again, is it not? Okay, because that means the polarity was the same as it was earlier, which means the slope has not, I mean this input signal has not yet been reached. Okay. So, what is necessary is a changeover. that the polarity of the quantizer changes from what it was, what is has been recently, okay, which happened here at this instant. At this instant, the signal amplitude was a bit less compared to the quantizer output really. So, how much difference was there between the signal actual signal value and the staircase approximation from the delay unit? Very small. Okay. What I am talking about is what is the maximum difference that is necessary, that is allowed really for this changeover to occur, changeover in polarity to occur, and that maximum difference is not 2s but s. Okay. Okay. I mean, you can explain it once again if you draw this waveform in a different manner. The way I have drawn, I have reached here basically, the signal has started dropping really. Okay. If I could draw it here, somewhere here, perhaps it would be clearer. Try drawing yourself really. The point simply is that if the actual sample value is somewhere here and it is still rising, okay, if the staircase approximation catches within within a range of s or less than that, then in the next interval it is going to exceed that, and hence the slope overload is being controlled.
Without changing the value of s or the step size, how can we control this slope overload distortion? Because
we are trying to control it right at the beginning. That means we are assuming that the maximum slope of the input signal is known, and from that information I am adjusting my step size so that I do not face any overload problem.
now are we adjusting the step size accordingly?
So, the step size, if I have this, if I following that inequality, if I adjust my step size, then I will say that okay, because I do not expect any higher slope than dx dt maximum really. So, the step is has been already defined more than that. So, this kind of phenomenon will not occur at all.
So basically using that maximum slope, we are defining one step size which will remain constant.
Yes, because it is linear delta modulation scheme. So, I am trying to find a condition, okay, for the step size. I am trying to find the minimum value of s, minimum value of s. I know the step size is twice of that, isn't it? Delta is twice of that really. So, I am trying to find a minimum value of s which will assure that this kind of slope overload does not occur for that given signal whose maximum slope was known beforehand. Okay. It is not a very general situation. In fact, you may argue, sir, no, the input signal being unconstrained, how do you know the maximum slope? Yes, that is a point really, but there again I will say that okay, from study of the kind of signal like speech etc., you can get a fair idea. Okay. And then if I consider a slope value which is quite high enough, I can only say that it is highly unlikely, okay, or it is less than 1% or probable, okay, that there will still be slope overload when the signal is unconstrained. Yes, please.
For given frequency, the slope will be almost the yes, but it max will have a fixed value. It will not turn that value. What you can suggest?
But can you find that slope value? What is that value?
So why will the slope depend on the frequency? It will not depend on the frequency.
It does depend. His point was correct. See, when the signal is band limited, okay, is it not that any sharp change is inherently related to higher frequency content in the signal? Is it not? See, any sharp change in the signal, in any signal, implies that the signal does contain high frequency components, very high frequency components, it is rich in high frequency. If that sharp change occurs many times, very frequently there, okay. But if there is sharp change occasionally, then again theoretically there will be higher frequency components, transient will be there, but we can say that the power associated is being very negligible really if it happens occasionally, and if I cannot catch up occasionally, still it may still be acceptable. So, that is the approach which is being taken here. Yes, please.
Will be filtered anyway. We have an LPF in the beginning.
So, we are coming back to his point really. When the signal is band limited, it is not that the slope will be very, I mean it will be 90-degree kind of thing, certainly not. Okay. So, if I go for some amount of overestimation here, I can take care of the overload problem to a desired level. Let me put it that way. Okay. Towards that, what is done is, as I will be doing, I will take up a very simple example of a sinusoid being the modulating signal, very regular one, okay, and we will consider the maximum slope and then try to find out an expression for the signal to noise ratio. Okay.
So one question.
Yeah, please.
In the staircase approximation, the difference between two steps is delta or is it s?
Delta. Yeah, because we are uniformly following the symbol of delta as the step size. Okay, the quantizer output values are pluses and minuses. Okay, and hence the step size is twice of that, 2 of s.
So even in the staircase approximation,
Yeah, that's how the yeah. So previously, if the quantizer output previously was at minus s, now it will be at plus 8 if it changes polarity. So how much is the change? Twice, and that's the step size here. Is that okay? Fine. So we can just say that this is the condition which may be adopted for um, almost eliminating the slope overload problem really. Whereas as I noted earlier, that delta, the step size should be small if I have to reduce the granular noise. So let us see through an example where we try to calculate the signal to quantization noise ratio, okay, following the inequality that I showed just now, so that we assume there is no slope overload problem. Okay. Precise analysis of slope overload problem is somewhat is beyond our scope of discussion really. So what we consider is an SNR calculation, signal to quantization noise calculation, SQNR to be precise, for when the input signal xt is a very regular sinusoid. Okay. So that kind of sinusoid is sometimes known as single tone. A tone means a sinusoid of a particular frequency. You know that? Okay. So let xt be am cos 2 pi fmt. Okay. So the maximum slope is 2 pi am fm. Isn't it? That is the maximum slope. So a point to be noted is that the maximum slope depends on the frequency of the sinusoid as well as amplitude. And we had a question just now that whether the maximum slope is dependent on the frequency. Yes, it is dependent, isn't it? If we have a higher frequency component, higher frequency sinusoid in our signal, okay, through Fourier transformation, if we see that there is a higher frequency component, okay, sometimes at some point of time or other we can expect a higher slope. So to avoid the slope overload condition, our step size, half of step size s by ts should be greater than 2 pi am fm, or am should be less than s by 2 pi fm ts. I have a reason for taking out am. You can guess, isn't it? Because if I say that my actual input signal xt, which is band limited in any case, okay, is limited to a maximum frequency of say fm or f2 or something, then we can see that we expect a maximum slope for that if I have a signal which is very strong at that frequency f2 or fm. Okay. So for that the amplitude must be restricted, so that this product value which is equal to the dx dt is always less than s by ts. Okay. So if I follow this inequality, that means am, the corresponding peak amplitude, is less than s by 2 pi fm ts. I can say that even for this frequency of fm, which may be the maximum frequency you may like to choose for the signal, maybe 3.4 kilohertz for the speech signal, then am is this much, which puts a restriction to the maximum signal power. Okay. And what is the power, associated power? Because it is a sinusoid, I can say that the associated power ultimately is am square by 2 is s square by 8 pi square fm square ts square. Is that okay? Fine. So we have an expression for the signal power. What is left? We have avoided slope overload, distortion, and to do that we have got an expression for the maximum signal power. Okay. Then what remains? What remains is the granular noise really, because there is no slope overload distortion anymore.
F square by 2, was it not the average signal power?
Power in any case is an average parameter.
So the maximum average power.
Oh, yeah. Well, his question is this am square by 2 is the average power. Yes.
Not the maximum.
Okay. But why I am calling it as maximum power?
The maximum we can use.
Yes. The maximum that can be fed really without causing overload distortion. Okay. If you have a signal whose peak amplitude signal at this frequency fm, but whose peak amplitude is less than am, then that is not going to cause any slope overload. So the maximum signal power that you can feed to this modulator without causing slope overload is this expression. Okay. Well, let me come to this. Well, just a minute. Well, so we can say that slope overload distortion is avoided, okay, for the step size twice of s or delta as per that inequality, and then what is left is the quantization error or the granular noise, okay, effect of granular noise. So, I can say that the maximum quantization error now is restricted to plus minus s. Am I correct? Okay, when there is no slope overload problem, then now the quantization error again will vary between plus s and minus s. Okay, and let us just remember that the step size is twice of s. Fine. So, again somewhat similar to what we tried for PCM and DPCM, we can say that we assume that this quantization error is uniformly distributed between minus n and plus n's. Okay. So, what is the quantization noise power? Is the average of the mean square error. Mean square error, okay, is square of the step size, okay, by 12, del square by 12. I make this we have derived earlier. Okay. So, now delta is equal to twice s. So, in terms of s, I can say it is s square by 3. Okay. So, the quantization noise power I am noting here as by NQ is del square by 12, which is nothing but s square by 3. Now, here is a very important issue. Interestingly, it is not this total power NQ which is given to the end user at the receiver end, because my signal, desired signal, actually in the delta modulation scheme is oversampled. Let us briefly qualitatively see how it is. See, the input signal xt is oversampled at the rate of 1 by Ts hertz, where Ts is the sampling interval. Okay. So, the quantization error will change, isn't it, very fast at the rate of 1 by Ts or Fs. If I write Fs is equal to 1 by Ts at Fs hertz, and this Fs, the sampling rate is much beyond the maximum signal frequency, because the signal is oversampled. Okay. So, the noise power is distributed well beyond the frequency range of xt. Do you accept? Because if you just try to visualize the quantization error q, I am talking about q of t really, as it changes with time, it is limited between plus n and minus s, okay, but the error is getting updated very fast. So, if you go for some kind of analysis, you will find that the spectrum or the power spectrum of the signal stretches much beyond the signal frequency range really.
So that is the spectrum of the staircase approximation.
No, the quantization error. What is quantization error? Q of, let me use this analog symbol now, notation now. Q of t, how is it changing? Can you just sketch it? See, if I say this interval is Ts against t, every Ts the quantization is changing, quantization error is changing, is it not? So, it is ultimately between plus s and minus s, but it is changing at a very fast rate. Okay. Fine. So, I can say that this quantization error will occupy a larger frequency band, much more than the signal frequency band. So, a fair assumption, again some kind of approximation here, is that the noise power is uniformly distributed with a constant spectrum up to 1 upon Ts hertz, because it is being changed, it is being sampled, it is being updated at the rate of Ts, okay, as if the noise PSD is something like this. Please look at this diagram. It is something like this up to say a frequency of 1 upon Ts or Fs. This is somewhat approximate description. Of course, it need not be uniform that way. There may be variation, there may be a tapering off over here. It may spill over well beyond 1 upon Ts a little bit. Okay, but broadly speaking, okay, that okay, the noise PSD is constant over this. This is an equivalent description. We will see that sometime later after we talk about some kind of Nyquist filtering. Okay, whereas what about the noise that will appear at the output of the low pass filter? Please remember that we had a low pass filter in the demodulator, isn't it? That low pass filter bandwidth, how much should it be? The bandwidth of the low pass filter, okay, should be as per the bandwidth of the signal itself. Okay, so the purpose of the low pass filter was to pick up the desired signal. Okay, and now we can see, I mentioned that, we can visualize it once again, that indeed at the input to the low pass filter, what will be fed is the quantized staircase approximation of the signal, which will contain quantization error which stretches much beyond the filter bandwidth. So, I can say the amount of noise which will appear at the output of the low pass filter is not this whole amount of noise, not this whole amount of NQ, but a portion of that. How much is it roughly? If the filter bandwidth is up to W, yeah, is it not? Okay. So, approximately we can say that if the equivalent bandwidth of the low pass filter, I am saying equivalent because I am assuming a very nicely designed, somewhat theoretical designed low pass filter with a flat response like that. Okay. In practice it may be different, but it can have an equivalent description. So, if W is the equivalent bandwidth, we can note that it is much less than 1 upon Ts, like here, whereas 1 upon Ts is this much, then the noise at the output of the low pass filter will be the noise, this much of noise, which we may also call as the in band noise. This portion of the noise we will call as the out of band noise. Okay. So, the effective noise power at the output of the low pass filter, though the quantization noise power was NQ stretched over up to 1 upon Ts, the effective noise power which is going to affect the end user, the receiver, is a fraction of that, S square by 3. It is W by 1 upon Ts, as he said correctly. So, the effective noise power at the output of the low pass filter, this noise is the quantization noise, is the granular noise I am talking about, is NQ prime, okay, is W by 1 upon Ts times S square by 3, which is W times Ts times S square by 3. Is that okay? Okay, it is fairly like that. So, is that an advantage or a disadvantage? So, you should always put a low pass filter at the output of your demodulator, delta demodulator. If you have not done that in your lab experiment, please do that. Okay. Now, and the design of that low pass filter matters really. One should not design just a very casual second order filter really, because then you will pick up a good amount of noise, especially when the sampling rate is not very high. So, now we can find an expression for the maximum SNRQ or SQNR, signal to quantization noise ratio, without slope overload. Slope overload we have taken care of by selecting a value of S appropriately. So, the maximum SQNR that we can achieve now is the maximum signal power, maximum in the sense I mentioned, divided by the in band quantization noise power. I now emphasize that it is a in band quantization noise power, not the total quantization noise power in Q. Okay. For DPCM or PCM, we did not talk about this because the input samples were at the Nyquist rate. The signals were not oversampled.
So, but even then you would have got a factor of at least 2. 2, sir. Factor 2 would be there definitely.
In?
So, because the Nyquist sampling rate is at least twice the signal bandwidth.
In fact, that twice factor is contained in this discussion here. See, for this relative, finding this ratio of W by 1 upon Ts, okay, that twice factor gets cancelled here really.
So, in that should be only W by 2 Ts.
It is, the W also should be twice W basically. see, I mean, that's why I kept this discussion a bit vague, because we will come back to this discussion later on. Okay, this I said that this is the equivalent bandwidth of the low pass filter, whatever it is. Okay, what matters here in this discussion is the ratio. This also is the equivalent bandwidth of the noise really. So what matters is this ratio for this discussion. Okay, yeah.
Same amount of 1 by Ts is at least 2W for DPCM. I mean, as per Nyquist criteria.
My point is, let's wait till we discuss about the Nyquist criterion. It has been discussed in which in some other course very exhaustively. Then let's wait for that really. For the time being, it's the ratio which matters, isn't it? How much portion of the overall quantization noise power is going to pass into my low pass filter. Okay, and then this ratio maximum value with ideal assumption is this. Okay, we'll come back to this actual filter bandwidth when we discuss about the Nyquist theorem. Well, so the maximum SNRQ, one can now put the expressions, okay, and how much it is? In one form it is 3 by 8 pi square. Let me talk about this expression, times Fs cube by W times Fm square, where Fm is the signal frequency of the sinusoid. Okay, and to get an appropriate one, you can find you can put Fm equal to maximum frequency. You may also try to relate it to W. Okay, all those are subsequent things, but otherwise in general, for any signal frequency Fm within the maximum frequency range, the overall SNRQ maximum is 3 by 8 pi square Fs cube by W Fm square, where Fs is 1 upon Ts. Okay, so we can have an observation at least relating the SQNR with the sampling. Is there any problem? Could you note it down? Yeah.
Single tone case W will become FM.
I am not going to ultimately see what is more important in today's discussion is to get an idea about what is going to be the overall scenario really. Okay. Now for a particular sinusoid, you substitute W is Fm by 2 or Fm, you do that really, you get a specific one for a specific sinusoid. My point is to show that the SQNR in general, see this expression is valid for any frequency. The W cutoff frequency is defined as per the maximum signal frequency, but this Fm need not be the maximum signal frequency you are considering. Note that the way I considered a sinusoid whose peak amplitude is AM, frequency is Fm. Okay, that this Fm need not be the maximum signal frequency, which means you can have a larger amplitude signal of lower frequency. You can put F equal to F max there, that is a special case. So now I want to make this, keep this general, where if for the maximum frequency sinusoid you are finding a value, yes, put Fm equal to F max, okay, W equal to F max by 2 or whatever it is, okay, or Fm over there, and find this product. But this expression is valid for any intermediate frequency as well, less than F equal to F max. Now SQNR maximum is proportional to Fs cube. This observation I am very much bothered with here. So we could find that the signal to quantization noise ratio is proportional to Fs cube. What does it mean? It means that if, because as I said that to get a delta modulation output for DM and demodulation and modulation and demodulation, you should oversample the input signal. Okay, I really did not address about how much oversampling is necessary. Did I address? Okay, I said it should be much beyond a Nyquist rate really. Now here is some clue. We see that the signal to quantization noise ratio improves by about 9 dB if I double the sampling rate. Okay. So if presently I have a DM system designed for a sampling rate of 32 kilo samples per second, then if I think of, and if I find that the signal to quantization noise ratio is not sufficient, if I try to improve the signal to quantization noise ratio by increasing the oversampling rate, okay, we can expect a 9 dB improvement by making the sampling rate from 32 kilo samples to 64 kilo samples. That is the point. Okay, and that is what is not very appealing. I do not know whether you will agree with me. If you have done some calculation on the PCM scheme, etc., see we get a 9 dB improvement for doubling the sampling rate. Okay. And we can guess at least intuitively that if I bring down my sampling rate towards the Nyquist rate, or say 2 times the Nyquist rate, that correlation between two adjacent sample is not going to be very high, and hence the output quality of the signal is not going to be very good really. So, the sampling rate is not very close to the Nyquist rate, okay, but it may be say a few times, 4 times, 5 times, I mean 4, 5, these are some typical values really, 4 times, or 5 times, 6 times of the sampling rate. And then if I thinking of even doubling that value, I get a nominal advantage of 9 dB in signal to quantization noise ratio. Whereas for PCM, to summarize quickly, how much SNR improvement we get if I increase 1 bit resolution per sample? We can calculate I mean just for 6 dB improvement per 1 bit improvement in resolution, is it not? Okay. Now, for standard 8 bit PCM, what was the sampling rate? 8 kilo samples. The bit rate was 64 kilobits per second, isn't it? And we had an SNR of how much? How much was the SNR? Typically say 48 dB. Okay. Now, to have a 48 dB SNR from a DM system, okay, you should not think of a sampling rate which is much lower than 48, I mean much lower than 64 kilobits per second, kilo samples per second. It has been with that adaptive scheme really, it has been possible to achieve an SNR, acceptable SNR more than 40 dB when the sampling rate is somewhere around 40 kilo samples per second, 48 kilo samples per second. Okay. There are adaptive delta modulation schemes which will give you acceptable SNR even at about 32 kilo samples per second, meaning there were the 32 kilobits per second is the final output really. For a lower bit rate of 24 kilobits per second or so, the quality starts degrading appreciably. Okay. And DM at the rate of say less than 24 kilobits per second, something like 16 kilobits per second, is barely acceptable only for some limited applications. But those are all adaptive delta modulation schemes. With linear delta modulation, you do not get that much of high quality really. With linear delta modulation scheme, typically you may get good acceptable signal to noise ratio of around 40 plus dB if the sampling rate is more than 48 kilohertz, kilo samples per second, which effectively means your bit rate is 48 kilobits per second, 56 kilobits per second kind of thing. Okay. So, at a bit rate of, so now coming to the bit rate of transmission, at a bit rate of 64 kilobits per second, DM is no good. If you can really transfer at the rate of 64 kilobits per second, go for PCM, do not go for LDM kind of structure, because as if you had a 32 kilobits per second DM and you have doubled the sampling rate, the incremental advantage is SNR is going to be only 9 dB, whereas in PCM you get a larger advantage in every 6 dB improvement. Okay. So, yeah.
If we look at the serial point, it's like the final data transmission in the channel,
Right,
which is serial.
right.
So the frequency could be in the PCM would be said to be around above 64 kilohertz.
64 is one standard rate. Yeah.
So in that way, when we compare delta modulation,
Yeah.
that frequency,
Right.
so
At 64 kilobits per second delta modulation output, right?
so
The PCM performs better. PCM performs better compared to this LDM, linear delta modulation scheme. Okay. So, at any rate around 64 kilobits per second, if you can really transmit at that high rate, better go for PCM than LDM kind of arrangement. But if you have other problems, if you cannot transmit say at a rate more than 32 kilobits per second or so, this kind of DM with little bit of adaptation may be a good choice. Okay. So, DM works better mainly between 24 kilobits per second to 48 kilobits per second, just to give you some thumb rule. Okay. At higher rate, PCM is better. At lower rate, DPCM is okay at around 32 kilobits per second. Okay. So, with this we conclude our discussion on delta modulation. We will discuss briefly about multiplexing arrangement, and then we will shift to the next major issue of baseband processing, signal processing, more towards modulation itself. Thank you.